Please welcome moderator John Fortune and his panelists as they explore electrification and battery storage.
Good afternoon, Hawaii. My name is John Fortune, and I will be moderating today's session on electrification and battery storage. I work for a company called Swell Energy, conducting market development, and Swell is an aggregator for Hawaii's grid services purchase agreement programs on Oahu, Maui, and the Big Island for aggregating residential and commercial distributed energy resources, specifically battery storage, to deliver grid scale grid services as an opportunity to further electrification of our grids. I want to thank everybody for joining us today, as well as the Maui Economic Development Board and Hawaii Energy Conference organizers. Also want to thank Tricia Rolfling from Hawaii Pacific Solar, who invited me to be a moderator here. And let's jump right in and meet our panelists, starting with Charlie. Would you introduce yourself, folks?
Morning, John, and thanks to you and Tricia for organizing and leading our panel. My name's Charlie Vartanian with the Pacific Northwest National Labs, where I head up the development of energy storage codes and standards to support the development, primarily through the IEEE. Come to PNNL as a retired transmission planner. When I left that job, I joined an energy storage system manufacturer that actually delivered an 11 megawatt battery energy storage system to Hawaii wind farm on Maui, as well as a 1 megawatt battery energy storage system to Maui Electric Company. So have some experience with getting large battery energy storage systems connected out in Maui, and that was very educational and definitely informed some of my thoughts to discuss with you today. Thank you.
Thanks. Daniel, you want to go next?
Sure. Hello, everyone. Daniel Crotzer with Fractal. So at Fractal, coming to you from a role of software. So Fractal EMS, we provide the operating system that controls storage. So think of it like Microsoft Windows, plus you get the Microsoft Office suite of tools with us. We have a little over 2 gigawatt hours in operation. And as a background, maybe infamously, I was associated with the Kahuku battery that caught on fire. So for those of you that remember that, I was actually there. So lots of learning experiences that we could share about in this discussion and over the course of some beers.
Thanks, Daniel. And Scott?
Thanks, John. Aloha, everyone. My name is Scott Schalich. I lead development for Plus Power in Hawaii. Plus Power is a standalone energy storage developer focused on utility scale projects. Prior to joining Plus, I worked at Pacific Gas and Electric on their procurement team, helped them sign some of their first PPAs for storage. And then after that, worked for Intersect Power, working on utility scale solar plus storage projects in WEC. And now I've been at Plus Power for a little over 3 years, helping establish the company as a leader in the utility connected standalone energy storage space. At Plus, we take a data-driven approach to siting projects and utilize a vast technical team based out of Houston to guide all of our siting efforts. Since joining Plus, I've been working on Kapolei energy storage and helping lead the development. It's a 185 megawatt, 565 megawatt hour project in Kapolei, which is helping to assist in the transition of the island away from the AES coal plant. Thanks, John.
All right. So I just want to remind everybody we have about 40 minutes here today, and so the real topic today is how batteries can further the goals, the electrification goals of our utility grid, and we are going to be talking about a pretty broad spectrum of topics here. want to encourage folks who are already familiar with the setup here for the conference, as you are listening in to our questions and our responses, to add a question, heart the ones that you think are the most relevant, and we will circle back towards the end of this session to discuss some of the audience questions. But to kick things off, we've got a number of questions that the group is gonna respond to here, and so I'm gonna start things off and kind of offer this up to anyone on the panel here. What role do y'all see stationary and mobile EV batteries playing in electrification?
Well, I'll start, and it's going to be really interesting because EVs account for about 90% of lithium production. All right, so 90% of the cells that are created go to EVs. About 5% for consumer electronics and about 5% for stationary storage. Rough numbers, right? Those have evolved. So if you think about that, we're doing a lot of storage, but we could be doing so much more. Or you could look at it that we should just take advantage of what's in electric vehicles. I don't know which way it's going to play out, but we need to be looking at both, and there are certainly groups doing so. We're looking at both. So to the degree that we can keep encouraging renewables, we're going to need the storage to go along with it to smooth out that variance. And then we're going to probably need a little bit more coordination if we're going to take advantage of EVs. Those EVs, they're sort of owned, at least the intellectual property is owned by the car manufacturer. So it might be tough to get them to participate in like a virtual power plant. Might even need some government, some sort of governmental involvement. We'll see. But what's exciting about this industry is we're still not even approaching the amount of pumped hydro that's been installed. So there's about 25 gigawatt hours on the mainland of pumped hydro. So we're not even there yet with lithium. So there's a lot to go. It's going to be pretty exciting to see how this plays out.
And before we, I want to let Charlie, it seems like you were going to jump in. You mentioned, Daniel, virtual power plants. I think I want to make a note there. What do you mean by a virtual power plant as well? Just so folks on the call are familiar with that concept.
Yeah, so virtual power plant is an aggregation of typically smaller resources. That could be homes that maybe in a neighborhood or in a city, a town, that are put together and operated as a single entity. Could be electric vehicles, either within a region, a territory, geography, or like a brand of car companies could be all operated together. So yeah, an aggregation of assets where someone, whether it's a utility, grid operator, has access to dispatch those resources.
Great. Thanks, Daniel. Charlie, you want to jump in?
I wanted to throw out one thought, and that's that energy storage will be a useful buffer and integrator, similar to what the industry has learned about integrating renewables through ramp rate management, shifting, smoothing. As loads continue to electrify, we will see more variety and types of load. The other parallel to that is as control and information exchange improves, I think accessing dispatchable loads and controllable loads is a complement to that. And if we discuss standards, I'll touch on that. How do we really get controllable loads into the bigger picture, where we got a lot of insights on DER management. But yet, same tool we use for increased variability in resources, wind and solar. I believe we can aim a lot of those solutions as loads get more dynamic and interesting.
Yeah, and to add on to what Charlie was saying there, it's when I think about the main role of all these different kind of types of batteries that Daniel was speaking to, and different resources, at the end of the day, it always comes back to reliability and resiliency, and helping to continue. People are accustomed to the reliability standards that we've set in the industry, and we need to continue those as we integrate more different types of resources.
And Scott, I'm gonna turn back around and ask you. Thanks, folks. That our next question. Can you talk a little bit about, and since you're kind of coming from the big scale of battery storage, some of the advantages and disadvantages of stationary centralized storage and distributed storage, and with on Oahu, a key component, this idea of the AES coal plant retiring. How are utility scale and distributed energy storage helping to maintain that grid reliability?
Yeah, thanks, John. I think when I think about the kind of advantages and disadvantages and kind of how they interplay together, the way that I see it is that we really need to utilize all of it, especially to meet our 100% decarbonization goals. And I think both provide unique benefits to the grid. KES is a really large project at scale that's completely fully dispatchable. And what that does is give Hawaiian Electric a really unique project that can provide not only just load shifting capabilities, but grid forming, fast frequency response, black start, instantaneous responses to any issue that the grid experiences. And some of Hawaiian Electric's modeling numbers back in May showed that KES alone is going to help reduce curtailment by 69%. It's going to increase their ability to procure new utility scale renewables by 10%. And it's also going to support increasing growth of DERs. And as you take on all these other resources and better utilize DERs, keeping the grid balanced, and to my previous point, maintaining reliability and resiliency deep into the future as the penetration of renewables increases.
Thanks, Daniel. Charlie, do you have anything to add there?
Well, I would echo Scott. We need both, and you need both because depending on the grid, sometimes when there's a lot of load, you have generators that turn on, and then there's no transmission path for a renewable source to come in. So it'd be nice if you had some more local distributed renewable sources. So that's a real thing, happens all over. Hawaii was a trailblazer here, where if you look at the progression of storage, you start with frequency regulation, you go to spin after you realize how valuable it is for frequency, then you move on to either shifting renewables or mitigating peak prices, both of which are energy shifts. And both central and distributed can do that. So we need a mix. And going back to the first question, EVs will be a part of that distributed.
I'm going to make a case for centralized as the most available to provide grid support functions now, because in a bilateral contract, you can specify, and in cooperation with the interconnecting utility, call for example, inertial equivalent for larger systems, fast frequency response. Where for the retail generator to provide, though, there's a lot more. A general framework has to be in place, typically through retail tariff rules that apply broadly. And I think to bring those capabilities to Rule 14 is something that's going to take a long, well thought through process before, let's say, making any of that a requirement broadly for retail generators.
And I'll jump in here because since my company has contracts with HECO right now, I think the opportunity, under a solicitation process similar to what you might see through a utility scale deployment, is to kind of place the onus on an operator, an aggregator under contract to commit to an amount of delivered services from these aggregations of devices. I think there's definitely a layer of complexity with distributed energy resources because they're often doing more than just serving the grid. They're serving kind of customer needs. EVs are, folks are going to drive them around. They may not be plugged in all the time and available for these grid resources like a stationary system might be. And then those behind the meter battery storage systems are, often their first priority is kind of serving a customer's needs. Be that through demand charge mitigation for commercial customers, or Charlie, as you had mentioned, the time of use arbitrage, rate structure for residential customers. But I think there is still, an opportunity also at scale, as we've seen. We're talking about, 50, 100 plus megawatts of aggregatable resources on the island of Oahu alone. That's from stationary battery storage systems behind customer meters that have the potential to also provide that sort of grid scale resource. So I think I agree with everyone. Although I'm the moderator and you guys are really the panelists here.
One quick follow-up to that, and Daniel, to your point, I think the accessible opportunity for grid support are the largest systems, but the ultimate solution, if it does not access DER and controllable loads, you will not achieve let's say, not even optimal, but one of the better potential outcomes from electrification. But I do want to harken back to Commissioner Anthony's comments. I thought she gave a really pragmatic view. Whatever path you take, you better think through the cost implications and the cost recovery, who's benefiting and who's paying. I think getting that fully robust access to DER, again, that's a tougher nut to crack. But Scott, you have a company that's going to solve all these competing application stacked use cases, customer side of the meter, grid side of the meter, and plug all those in and you give us the answer, right? With your software.
Oh, I think you meant Daniel there, because I was like, yeah, we're very focused on utility scale here at Plus, but we hope that Daniel and John can pick up the DER piece. That's also going to be crucial.
Yeah, and in the future, some of the software that Fractal does, others like Tesla, etc. Yeah, we'll be able to economically bid and dispatch projects. I guess so. There's still a question about whether EVs, will be effective, right? And John, you mentioned, hey, well, if can't use an EV if it's not plugged in, right? That's kind of a key tenet to this. So, we don't yet know. There are only a couple of EVs that even let you modulate the way that they charge, right? So the Leaf, Mitsubishi, the F-150 is coming out with the ability to go bi-directional, and we'll see how well that works. I hope it works really well, but I would say it's still up in the air.
Thanks, Daniel. Let's kind of jump in then on EVs, right? Because let's kind of double click on this. Right now, there are kind of three modes of potential: these V1G, V2G, V2 home, right? These ideas that these EVs are going to be able to provide some resources to residential customers, maybe through fleet applications. So Charlie, I'm gonna jump back to you. How effective are these EV vehicles, and how do they actually work in terms of what are they allowed to do today on the grid versus what do they need to do to really become one of these sort of more dispatchable resources, and how do they compare in terms of battery sizes to some of the commercial stationary storage systems we see out in the market? Those are three questions.
But what's doable today is almost nothing. Number one, battery warranties are an issue in North America. So the Nissan Leafs that are used as virtual power plants successfully in Tokyo, dispatched by Tokyo Electric Power, can't discharge for anything other than turning the wheels. That being said, I think every company is looking at it at least as emergency home backup is probably entry level. But here's where the guy working from the standards area says, wait a minute, as soon as you can parallel to the grid and stay paralleled, you may be subject to IEEE 1547. And if you can impact the grid's performance, you certainly should be. So a commercial for a new IEEE recommended practice 1547.9, applying 1547 to energy storage as an annex on V2G. When is it in scope? When is it out scope? And it points to the SAE standards that are being modified to get ready for V2G. And here's the key thing. In North America, it looks like that capability is going to be enabled at the stationary charger, not the onboard charger first wave. I think that's okay because almost any car can be controlled to discharge under the appropriate command. And then it's up to the stationary charger to slice and dice that, both real and reactive, to deliver a grid service. But we're many steps away, both on the commercial side, battery warranties, as well as getting the grid standards in place for vehicles. That being said, P&L is doing two demos with utilities. Their concern is large-scale fleet charging. I'll say it's a concern now, but they're all respecting that you turn that around, it's an opportunity. Because you do get the multi-hundred kilowatt, even with a couple light-duty vehicles, but you get 10 electric buses there with 200 kilowatt dispatchable capacity. You got a megawatt resource, tens of megawatts in some cases. So they are relevant, I think, as a distributed energy resource. They're also a great candidate to get at the VPP and aggregation opportunities. But it's over the horizon. It's going to take some breakthroughs. No breakthroughs in science. All the technology's there. It's getting the rules and regulations in place.
We're talking 5 or 10 years out. Like what's your crystal ball say?
I've learned never predict a regulatory process. We worked on AB 2514, John. We know that.
Yeah. And then let's talk a little bit about the scale. Like how many megawatt hours does a home or business need to have power for a few days? And how many are kilowatt hours? Let's maybe use the F-150 as an example. I think, which is something like 100 plus kilowatt hours, right? In the battery. We're seeing these Tesla EVs, and I'll say that a Tesla Powerwall on the other side of the equation with a stationary battery storage system is about 13.5 kilowatt hours. It's about how many days do we think that a fleet of buses could provide power to a commercial load or an EV could provide in those outage situations?
Well, for a home in a somewhat moderate, like let's say 80, 90 degree weather, you're using about a watt per square foot, right? So 2,000 square foot home, 2 kilowatts continuous load, right? So that gives you, and that's basically saying that half the load is HVAC. That's about 50 kilowatt hours a day. So that F-150, because I think the F-150 gives you like 75% of that 100 or the 130. So whatever that math works out to, right? Approaching 2 days. But if you're a little bit smarter, or if it's the winter and you're using natural gas as your heat source, you could go a week, depending on how much you conserve.
And Scott, what do you see as this sort of the scale that we're talking about when we're talking about utilities in terms of the direction that we see these megawatt hours heading at the utility scale?
Yeah, I mean, in terms of the EVs, it's not really my sweet spot, but I definitely am in line for an EV myself. So I would hope to participate in some of these markets in the future. But yeah, on the utility scale, I think it's the megawatt hour and the scale that is required is really looking at kind of getting into those sort of outer edge cases of really providing that resiliency, so that if there is some sort of major portion of the grid that is down on the transmission side, that we can still provide enough megawatt hour scale to keep all the homes powered, and maybe start dipping into those demand response kind of categories while maintaining the vast majority keeping the lights on.
Real quickly, at the other end of the scale, Nissan Leafs combined with vehicle to home ready chargers by Mitsubishi can keep homes. And here's a key thing. Smart grid is moving down at the grid edge. You separate an emergency and a non-emergency panel even at the home level. You put up some PV and you can sustain a minimum amount of, let's say, home emergency load, electrical load indefinitely. 95% confidence you can meet minimum load. And here's, John, how long will it be? Well, the technology is here today. Vehicle to home in Japan was driven by Fukushima. The government basically directed Mitsubishi, a couple other companies, to work with the car manufacturers. So the Mitsubishi Nissan Leaf combo, massive success, vehicle to home backup, as well as aggregatable as VPP being dispatched. And Arlington Microgrid by Snohomish PUD are using 2 Leafs and 2 of these Mitsubishi chargers with a full complement of capabilities as a demonstration, and running them through their paces now as an example. So we have examples around the world, a lot of the Scandinavian countries accessing these capabilities, but a small amount. And here's the other beautiful part, that charge is ready to connect PV at the DC, rail, stationary storage if you want more backup, and the car. So it's an entryway to a DC microgrid. And I know Hawaii's worked at some DC low voltage connections. And again, so at the other 20 kilowatt hour battery, you can do a lot with it at the consumer single meter scale.
I think it's probably a good point to note, in terms of grid reliability, I think most networks might experience, probably less than a 2-hour outage on the regular, although we are seeing some as climate change kind of comes into the picture, and we're seeing new issues crop up. In California, we now have the power supply shutoffs that could be for multiple hours, even potentially multiple days during the high fire threat zones in certain regions. So I do think that reliability is probably a big consideration for a lot of folks contemplating investment in these technologies. But let's kind of jump back a little bit. We talked a little bit about lithium ion, and I think that's what we're seeing a lot of these EVs and stationary smaller scale storage systems. The types of technologies. What other technologies are out there for battery storage, and what are the environmental risks associated with those different chemistries?
I'll jump in. So there are a lot of storage technologies, from mechanical to electrical, and then batteries being chemical. I've been in the storage industry for a bit now. We were using lead acid batteries before there was lithium, right? We've kind of held our breath and then got tired of holding our breath for flow batteries. So between flow, zinc air, I just don't see them proliferate like lithium, because you have lithium in your car, in your laptop, in your phone, and lithium just now has this built-in advantage of economies of scale, and it's going to be really tough to catch up to that. I really hope that there is a different chemistry out of the ones we know about that will become economic, but it's like lithium's just pulling away and they're not catching up. Then you come upon things like gravity, compressed air. We know about hydro. So we've built a lot of hydro, but any new hydro is very marginal, meaning very expensive, because all the good places are already taken, right? So good places are gone. Now it creates a lot of earthwork to create either a lower or upper reservoir. So that's expensive. And then probably the biggest hurdle is just permitting to do that type of earthwork, right? So that's tough. The physics of the gravity and the compressed air, when you mix the physics of those two with the financials, they don't make any sense whatsoever. I mean, it's not even close. Like it shouldn't even be considered, even though there are startups now that they're trying to do it. I mean, it makes no sense. So we circle back to lithium, and so then is solid state going to be a factor in the next few years? Is CATL sodium lithium going to be a factor? I hope so. I guess where I would go is, I have a love-hate relationship with Elon Musk. I love to hate him, but I respect him. I would take a look at anything that he's taken a look at, and right now that's just lithium, and it's the NMCs and the LFPs, and that's what's usable right now.
Yep. Daniel and John, on a little bit longer time horizon, but there's a little bit of overlap. I'd say on the 5 to 10 year out, Pacific Northwest National Lab is working on sodium ion, aqueous organic flow batteries. And an exciting area to me is the zinc alkaline, zinc manganese oxide, and zinc air. And even good old lead acid. Daniel, you've had some experience with that. But here's the issue. Yeah, from a commercial standpoint, the costs are going to have to come down. Now, the two drivers are longer duration with earth abundant, relatively low environmental impact. So that's fits these well. And here's a couple targets. So at a 5 to 10 year out, we're looking to get to the 6 to 10 hour discharge. That's economic at a 5 cents per levelized cost of storage. And if you match that with 5 cent levelized cost of energy from PV, you have a pretty darn cost-effective resource, especially in a market like Hawaii. There was a question that I do want to highlight, and Scott might want to chime in on this. Someone asked, well, when is it a firm resource? I'd say there's good experience today to say if you can get 4 hours of discharge from a grid reliability standpoint, the grid operators have time to redispatch, make changes. And in California, resource adequacy has a robust framework for why 4 hours, and 4 hours is used for firm capacity credit. So that's a benchmark. But for Hawaii, if you have an abundance of PV and you can shift and move it, what Kauai Island Utility Cooperative has done with PV and storage, I think points to a little longer duration. Now, you go out 10 years at what the labs are looking at, then weekly and seasonal are interesting. You get more into the electromechanical or really interesting chemical storage options. But sodium ion, nickel air, and some of the flow batteries have a mixed record. I worked for a vanadium redox company. Some promise there, but 5 to 10 years out, lithium's going to dominate on cost. But at this, I'll bring it up. Safety is a concern, and I think lithium's better off in a centralized, managed industrial facility than a bunch of lithium battery systems in garages until some of the safety issues are sorted.
Yeah, and let's kind of double click on that. So we mentioned NMC, which is nickel, magnesium, cobalt, right? And LFP, lithium iron phosphate, right? And we've been hearing about this transition with Tesla to LFP batteries. Why is that? What's the difference between those two lithium chemistries that makes that's important for the audience to understand?
Yeah, So historically, LFP has been a chemistry that has had better performance than NMC. So longer, more cycles, deeper depth of discharge. So basically a more usable battery that lasts longer. Where there's a little bit of a battle is that NMC and NCA, which is a cousin to NMC. So think a little bit more cobalt, a little bit more aluminum. It's more dense, right? So you can create a battery pack in a car that has more kilowatt hours, and so you can offer an electric vehicle with 300 miles of range, and be able to build it to where it looks reasonably cool. So what was happening is that NMC, the cobalt variant, just was being built more because it was more dense for the EVs. What's happened lately is that the Chinese companies have really been effective in getting better density. So now, instead of a iron phosphate battery being twice as big and then becoming only 50% as big, well, now when you include liquid cooling, it matches the density of NMC. So that's really what's happened. And so now you have the same density and better life, and deeper depths of discharge. So that's where Musk is going. That's where Rivian's going. So they're going to take advantage of these progressions, these steps in technology for the LFP, and so we'll see more of it. And just one quick thing, you could argue that LFP is tougher to catch on fire. Okay, and I use very specific words there. Tougher to catch on fire. When it's already on fire, it lights up like fireworks, like any other lithium battery, but it is tougher to catch on fire.
All right, thanks, Daniel. So I'm gonna turn back over to Scott, and so I'm going to answer or ask one of these questions. And I think, Scott, you may be the right person to answer this. So there's a recent state bill in Hawaii that is sort of requiring this idea of firm renewables, this sort of 24/7. The definition of firm renewables is this ability to provide that power 24 hours a day, 7 days a week. How much battery do we need to firm up? For example, a utility scale solar project, maybe a 1 megawatt system. Like, what are we talking about in terms of long duration battery storage? And is that are we at the case where that's economically feasible? 1 minute.
Got it. Yeah, I mean, I think that is. I wish I could answer that exactly correct today, because then we could we would be able to look into the future. But I think to Charlie's point before, 4-hour storage like what KES will provide is very firm, especially at that scale. Now, as you look at all the edge cases, 4 hours, even 6 hours, even 8 hours isn't going to solve some of your edge cases. And that's where I think technologies that are trying to crack the nut of multi-day storage come in. And I really applaud Hawaiian Electric for right now. They're exploring these types of technologies. And in terms of whether or not will they pencil today, I mean, that's exciting technologies out there that could potentially provide some of this more firm.
Awesome. Thanks, Scott. Well, we are almost at time here, so I just want to extend my thanks to the Maui Economic Development Group and the Hawaii Energy Conference, as well as my panelists, Scott and Daniel and Charlie, for joining us, and for everybody who participated and offered your questions. Sorry we weren't able to get to all of them, but hopefully we answered quite a few of the ones that you had burning for you. And guys, any closing thought?
Oh, thanks, John. Thanks,
Thank you.
everybody.
Yeah, I think Hawaii in general, because you've led as far as storage. I could credit you for helping Fractal to get started. So keep leading, keep innovating, keep pushing the envelope.